arguments are needed, which is what we did in the previous case. And that's what Lab 3 asks you to do, is use it as a fixed size array of character pointers. Now we're going to relax that assumption and say, well, I don't know how many character pointers I need, and so the size of names is going to vary. Still have the same setup as before. We have the size of buffer, a temporary holding place to read in a string. We have num names, which keeps count of how many we have. We have names, which is a char star star. And now we introduce the notion of temp, which is a char star star. And the idea here now will be allocate an array of, say, three character pointers. Allocate that. Fill up those 3. So I've got an array that's 3 long, each one pointing to a character string. Now I read another name in, and what I have to do is allocate an array of character pointers that is 4 long, copy the first 3 in there, and then allocate the memory for the 4th name, 4th word, whatever, and place its address in the 4th element. This 4th element is pointed at by temp. This array of 4 is pointed at by temp. We fill it up with all 4 things. And once we have temp pointing there, then we can delete the array of pointers that names is pointing at and have temp point at the new one. Okay. That's a mouthful. It's a lot of things going on there. Let's see if we understand what I just said. So temp, starting off, new char star. How long is it? Well, num names is the number of names. It's going to be 0. And so we allocate an array of 1. An array of 1 character pointer. And place it in temp. We copy the address in there, and that assumes that there's something to copy. Is there something to copy? No, not starting off. This for loop is skipped because num names is 0, and 0 is not greater than 0. So we skip the for loop the first time. And moving ahead, assume that we have names has these 2 addresses in it, pointing at those 2 strings that are already there. We add a third one. And since temp has grown, I thought there was a picture here. Since temp has grown, we copy these 2 addresses into here, into the first 2 elements of temp, and get the third one, the new one. So now temp points to this, this, and this. And now we can delete this array, can't we? Because these pointers are duplicated over here. We don't erase this and we don't erase that. We just delete this array. Questions with that? So as a result, we have names and temp both pointing to this array of pointers. These were never moved. I'll get back there eventually. These 2 were never moved. They were never removed either. They're the same as they were. We just changed what array points at them, which we copied their addresses over into this new array. Okay, any questions on that part? I want to go through how to do this and all of that. But any questions on the concept? all got it, huh? Okay. The next thing that I want to introduce is this notion of moving ahead into chapter 13. The notion of structures. Some of you have been chomping at the bit to talk about and work with and deal with objects, and today we start that process. A structure and an object are one and the same thing in C++. They are exactly the same thing. They do exactly the same thing, except one important thing. And that thing has to do with whether or not the structure is public or private. If it is an object, it is private. If it is a structure, it's public. Now, what do those two terms mean? Public means anybody can get access to it. You don't have to be a particular class of things to access it. Anybody can get to it. Private means that you have to belong to a certain class. You have to be an upper class or a middle class or a lower class or something. You have to belong to a certain class in order to access it. All of that is controlled through the linker and not something we need to worry about just now. But the notion of a structure and the notion of an object are the same in C++. In C, we only had structures. And so what Schustrup did is he expanded the concept of structures from C when he was writing C++, defining it, and said, oh, an object can be the same as a structure, will be the same as a structure. No need to invent new syntax. We'll just change a few of the constraints on it. All right. So structures are incredibly important. We've been doing structures for a long, long time, a lot longer than we've been doing objects. And so they're very, very important to this notion of dynamic data types, this notion of structures, data structures. By the way, the term struct and structures refers to something very specific in C and C++. Data structures refers to something more generic, right? Just a concept. Syntax for a struct or a structure is the word struct, which is a reserved word, the name of the structure, make up a name, it's a variable name, and the data members with curly braces around it and semicolon after it. So if we look at this one, here we have a data type. Now this is not a variable declaration. It is a data type. So since it's a data type, this is not a memory occupying statement. We don't allocate any space here at all. All we are doing is defining, and I'm using the following term very loosely, we're defining a template for how we want our memory to be carved out when we actually declare a variable. So we're going to declare variables of type student. So just as we've seen before with integers and chars and so on, we're going to be able to say now student, oops, I'm going to do it there, I'm going to do it here. Student space Q. what I've just done is declared and defined a variable of type of Q. The variable name is Q, and it is of type student. We call this a user-defined data type because now we are creating the data type. We are creating it from primitive types, these over here, integer, char, and float, but nevertheless, we've got a brand new data type called student. Think of the struct as a cookie cutter. I just make my own special cookie cutter, and I've got all this memory laid out, dough, and I take the cookie cutter and I stomp down, and I just carved out of memory something that looks just like this in terms of structure. Now, there isn't actually anything in there yet, is there? There's no data stored in there yet. So we need to learn how to access that data. And so what we will do is we'll say Q dot ID equals, and that's a lowercase I, equals some number. So the dot notation now gets to be introduced. Q is a static variable, not allocated dynamically, but static variable. And we reference the sub-elements of Q by using the dot notation. Clear? Questions with it? This is moving along really quickly, so you guys have been reading ahead, perhaps, I hope. In any event, if I want to get access to fname, I can say Q dot fname. Now, how will I put something in it? The variable has already been declared. By the way, what's the name of the variable? Tyler?
Fname?
Nope.
Or
Q.
Q. Oh, Q.
Q is the name of the variable that I'm working with. It has an element called fname, which is an array, and we know that we can't just simply assign one string to another string, so we have to do a string copy. So if I want to get Tyler placed in fname, then I'm going to have to do something like strcpy. That string copy comes back a lot, doesn't it? We use it an awful lot. String copy and then quote, Tyler, close quote, like that. Is that clear? Now, if I did something different, not knowing what I know, I would just naively wanted to do a shallow copy, right? A shallow copy, I can do that. Looks cool, doesn't it? Shallow copy taking the address of where the string constant Tyler is stored in the constant table and placing that address in here. Okay? Better to do something like this. And if we had, for example, another variable that had Tyler's name in it, stored in buffer, this is just a standard garden variety string copy, isn't it? Is that clear? Questions there? Well, I have a single valued variable called Q, but let me do student and let me call it X and do 100 of these things. Now what I've done is an array of these structures. Each one can hold an ID, an F name, an L name, a character gender, and a float GPA. Is that clear? So whatever I can do with a primitive data type, like integer, char, and so on, I can also do with a user-defined